Welcome, aspirants. It's great to have you joining us for today's crucial explainer, right here at Rungta IAS Academy. I'm joined by Madam today, and we're going to tackle a highly relevant and frankly urgent topic for your GS Paper 3 Disaster Management syllabus. We're looking at the growing crisis of urban electrical fires.
Thank you, sir. Exactly. And to make this as useful as possible for your preparation, we've structured today's session to perfectly mirror the ideal framework for a UPSC mains answer. We'll start with the context of these urban fire disasters, move on to unpacking the root causes, then we'll identify the critical policy gaps, and finally, we'll wrap up with the way forward and practical solutions. Let's dive right in.
Right, so starting off with part 1, setting the context for these urban fire disasters.
Now, as you all know, a stellar mains answer absolutely must be grounded in recent current affairs. Just look at the tragic Vivek Vihar building fire that happened on May 3, 2026. It claimed 9 lives, and it's suspected to have been sparked by an AC short circuit. These aren't just statistics, aspirants. These are the real-world stakes you'll face as future administrators.
Absolutely, and please note down this next data point. For your exams, it's absolutely vital. On April 25, 2026, India's peak electricity demand hit a record-shattering 256.11 gigawatts, right in the middle of a brutal 47-degree heat wave. Just cooling demand alone pulls about 50 gigawatts. This kind of exponential surge is putting an incredibly severe stress on our urban power grids.
Building on that, if we look at data from the Delhi Fire Service, they attribute over 80% of fires in the capital directly to electrical faults. The Mumbai Fire Brigade reports very similar, alarming numbers. Make no mistake, this is the absolute dominant cause of urban fire disasters in India right now.
Which naturally brings us to part 2 of our answer framework, unpacking the actual root causes behind these incidents.
The core structural problem we're facing is rapid load growth on entirely obsolete installations. Think about our legacy housing stock for a second. You have a simple fan and bulb circuit that was maybe installed back in 1985, and today it's being forced to carry the heavy, continuous burden of a modern 1.5-ton inverter AC. The original wires were simply never sized for this kind of load.
Exactly. And here's a crucial technical point. Mentioning the concept of harmonics in your GS3 paper is definitely going to fetch you those extra marks for technical accuracy. You see, modern inverter-driven ACs don't draw current smoothly. They draw it in jagged pulses, which injects distortion at multiples of 50 Hz. This process quietly and dangerously heats up the neutral conductor, which is a wire that was just never meant to bear that kind of distorted electrical load.
Right, and when you combine that severe harmonic distortion with a loose connection somewhere in the panel, you create a deadly hotspot. It silently burns away the insulation over a period of months until eventually it ignites. Tragically, this exact combination was the root cause behind massive disasters like the SUM hospital fire in 2016 and the AMRA hospital fire back in 2011, which claimed 117 lives.
This leads us directly into part 3, identifying the systemic policy gaps that allow this to keep happening.
We have to ask, why does our administrative response remain largely reactive instead of proactive? Well, the most glaring gap is in our data and forensic capabilities. Currently, the NCRB just dumps thousands of fire accidents into a generic catch-all other category. Why? Because we are facing a staggering 96% shortage of fire forensic infrastructure in this country. So instead of proper root cause analysis, we are relying on provisional guesses.
If you look at global benchmarks, the contrast is really stark. For instance, in the US, arc fault circuit interrupters, or AFCIs, have been mandatory in residences since 1999. These devices actually cut the power before a dangerous arc can ignite a fire. In India, they're practically absent. On top of that, we completely lack a formal certification regime for modern IoT sensors, like Ting sensors, which can detect that dangerous microarcing early on.
Moving on to the final part of our structure, Section 4, the way forward and solutions.
Aspirants, I highly advise you to replicate this exact set of macro policy recommendations in your exam conclusions. First, we need to mandate IEEE 519-style harmonic compliance for all new building approvals. Second, we should introduce a strict periodic inspection regime modeled after Japan or South Korea. Third, we must build a transparent, published forensic chain similar to the NTSB model. And fourth, we have to harmonize our completely fragmented data sets across agencies like the DFS, NCRB, and BIS.
And at the micro level, administrators have a duty to encourage and enforce consumer safeguards.
We need to insist on ISI-marked wiring and proper breakers. Citizens should be educated to never run an AC on a shared, undersized circuit. We should be advocating for thermography scans of main electrical panels every 2 to 3 years, and of course, ensuring strict annual AC servicing. Building community awareness is absolutely vital for a truly holistic mitigation strategy.
To wrap up today's explainer, I want to leave you with a challenging mock UPSC interview question to really test your application of this material. Think carefully about this. As an administrator, how would you balance India's exponential cooling demands with the critical need for disaster-resilient urban infrastructure? Ponder on that. Thank you so much for joining us today at Rungta IAS Academy. Keep studying hard, stay focused, and we'll see you in the next explainer.